Yeah, so you asked a good question. So I have changed the notes. I still have to upload it. So basically, this is an example, right? This 1 over x minus 1. So what you can show is that 1 over x and 1 over x minus 1, they are the same up to unit multiple. So for example, if you look at valuation with respect to 1 over x minus 1, then this is the identity. 1 over x minus 1 is equal to unit. So this thing is a unit modulo this times x. And similarly, you can also show that if you look at the valuation 1 by x, then again there is a reverse identity. So in both the valuations, basically what it means is that the maximal, unique maximal ideal can be generated by both. So yeah, so x minus 1 inverse and x inverse, they give identical valuations and they give the same DVR. So for that, actually I had to also change the proof slightly. So case 2 was not properly studied before. So you divide into two cases. One case was that x is in R. So let R be a valuation range. And we are looking at the function field with the transcendental element x. Right? So we are looking at the projective line basically. So then you divide into two cases, whether your DVR contains this variable x or not. So the containment of x gives you irreducible f, and the non-containment of x gives you 1 over x.
Okay, so the K is not algebraically closed, and we'll have R of like different degrees, like x square plus 1, those kind of things are x square plus 1 inverse will also come, right?
Yes, yeah. So f is an irreducible polynomial in one variable x.
Because it is algebraically closed, that's
Correct.
why I'm saying this.
But this proof is written also in general, so we don't assume.
The case one is clear, even for general, but
Yes,
below
and
this,
in case 2, so since x is not in R, R is a DVR, so its inverse is in R, which means that k of 1 over x is also a subring of R. Now from the above case, yeah, the unique maximal ideal is generated by some polynomial in 1 over x. Now the only observation which was missing before is that x inverse is not a unit in R, because if it was a unit, then x would be in R. But we are in case 2, we have assumed that x is not in R, which means that x inverse is not a unit, which means that it's in the maximal ideal, which means that f x inverse divides x inverse.
what degree are that?
So they are the same. They can be different only by a constant multiple. So that's it. So this part previously was muddy. Now it's fine. Yeah, so x, when you look at x minus 1, x minus 2, actually you get this property. Somewhere I have added, yeah, this property you get in blue. So 1 over x minus alpha for any constant alpha, they give you same valuations. They are all generators of the principal ideal. That's the example. Yeah, we had not observed this before. It's not a contradiction, it's fine. Okay. So then I guess we can start. Any questions from this part? Yes, so we have shown that the zeta function is a rational polynomial in T, and we can think of this as the analytic continuation of the power series. So we can now just use that, let's say GT over HT or AT over BT as the function which is defined over all complex values of t, and it defines this and it satisfies this functional symmetry equation, t replaced by 1 over qt. We have this relationship. So we did this, and hence we also get, in classical form we get this zeta of 1 minus s related with zeta of s via norm of the canonical divisor, canonical class, divisor class. We have information about poles. Yeah, there was one typo here. The residue of not zt but q minus 1 times zt. Okay, because we had already multiplied our z with q minus 1. So the residue of zt is actually class number divided by delta times q minus 1. Okay, that came from the happened in the formula. Residue at t equal to 1.
When you say residue, you mean the integral?
Yeah, by residue I mean you have a univariate polynomial, you multiplied by t minus 1 and then set t equal to 1. So the answer that you get, that is called the residue. Or in other words, you have a polynomial f, you can first divide by t minus 1, get the remainder, I mean get the quotient, and then in the quotient substitute t equal to 1. But yeah, I mean we can, here it's very explicit, so don't have to think of integrals. The motivation comes from there. So now the final thing is to deduce that delta is equal to 1. So for that we need this base change theorem. So let's prove this. Yeah, so we want to relate the zeta function of Cn, which is the same curve in a higher field, with C, which is the curve defined in constants finite field FQ. So by Euler product, it suffices to compare the two sides for a point P on the curve. And its conjugates in the curve Cn. Okay, so the picture is that you have the curve C and then you have the curve Cn. So points on the curve, when you go to the same curve but higher field, the point may actually ramify or split and give you more points because you have a bigger field. Well, so the problem is that the point P is actually not a real point, it's a prime ideal. So essentially the prime ideal factors. So the prime ideal may factor, so the cloud of points factorizes into smaller clouds, which are again prime ideals in this Cn. So a P here may give you Q1 and Q2. This is what is happening. So yeah, we will see that the part of P on both left hand side and RHS behaves as claimed. and then by Euler product you can take the product over all the points and you will get the theorem. So let's only consider this point P now.
So what's the Euler product?
Euler product is that the zeta function factorizes into according to primes.
Can't you prove this directly from the series? X of sum over. Just plugging stuff which you
There is no exp.
So Z of E is X of sum over the point curve.
Yeah, but there is no exp. We haven't defined that.
That's not the definition you used.
Obviously not. Z t comma c is just sigma t raised to degree of divisor.
Then you will show the two are equivalent.
Sure. So the definition we started with is basically it follows the ordinary Riemann definition, which is sigma 1 over n to the s in the case of numbers. So we are just using the same definition, analog of it in curves. The thing you are saying we will deduce after this theorem. But anyways, the main technical content is actually the same, which we will see now for a point. So what is happening there? So for this point, yeah, so let's just fix point P for the proof, we will not change it. So let MP unique maximal ideal of the DVR corresponding to P. P is a smooth point, so its germs basically give you this local ring with unique maximal ideal MP. So this is a DVR, that's the DVR data. And the data gives you this field RP mod MP is a finite extension of K, right. So Kp is the field where actually Kp is the field I think where P completely splits, and it is still a finite extension of K. It sits between FQ bar and FQ, if K, so K is FQ. So Kp basically Kp has this model Kt mod F. Is an irreducible polynomial. Over FQ, right. So this is just the description of where the point completely splits. Yes, so what did we have? We had this field K prime. So over this field K prime, which is slightly bigger, it's bigger than FQ, it's Q to the n size. So what will happen over K prime? F may split further. No, not that. Yeah, okay, fine. Yeah, so F is an irreducible in in KT, which is FQT, but when you go to FQ to the n, F may split. And let's say it splits into E polynomials, E factors. So what can you say about the factorization? So Ft splits into E factors over the new field. They are irreducible now over K prime. So F splits into F1 dot dot Fe. So what can you say about them? So it's not difficult to prove. Just use finite field properties. You can deduce that F1 to Fe, they are mutually co-prime. Their degree is the same, and something about E you can say, which is essentially whatever was the degree of F, you take the GCD of that with N, that will be E. So Fi's are co-prime. Their degrees are the same, and E is nothing but the GCD of N with the degree of F, which is also the degree of the point. Is that clear? So as an example, if you took an irreducible x raised to 6 minus alpha, then so this is suppose the irreducible over Fq. So what will happen when you go to Fq square? So when you go to Fq square, then essentially this degree 6 will split into 2 degree 3. Each of them will be irreducibles. So x cube plus minus square root of alpha. Okay. Also, if it was just x square minus alpha that you had, then x square minus alpha will split completely when you go to Fu square. And for any other even degree, it will just split into the degree divided by 2 factors. So this can be shown easily. So those are the properties of the essentially the min poly of the point when you go to an extension. What does this say about the zeta function now? Right, that's what we have to deduce. So what it says about the point is the point P corresponds to E points Q1 to QE in Cn. Such that the degree of the point is equal to degree of Qi, and all these degrees are the same, so it's E times d of Q1. Okay, so you can rehash this polynomial factorization into our degree operator on the point. So essentially what is happening is that this point, which was a prime ideal in Fq, when you go to Fq to the n, it gives you the prime ideal factors into prime ideals in the new word, in the new field Q1 to QE, and their degrees are the same, which then will be equal to d of P divided by E. Right, this is an equivalent formulation at the level of points. So, what is the contribution now to the zeta function? Let us check that. Thus, the contribution in z t raised to n Cn, which is the left hand side of the theorem, so that the contribution coming from the point P is this. Do we believe this? Why is that? So, t raised to n comes for free because we have already substituted t raised to n in the zeta function. Degree of q1 is dp by e, so that is in the exponent, and the contributions are coming from q1 to qe, and they are the same contributions, so we have multiplied that. Right. So, corresponding to P, when you look at the conjugates which split above, when you go to Fq to the n, you get these E factors in the product. Right. This we can say is the contribution, exact contribution coming from P in the left hand side. Is that fine? We have to match this with the right hand side. So, for that, what we will show is the following identity. Yeah, so the above expression is just 1 minus t raised to n dp by e raised to minus e. So, we want to now study that expression. So, that expression with e in the exponent, we want to see how it factorizes, and that's, once we show this claim, you can now fit this in and see that the RHS contribution is the same. Right. So, what we basically have to show this factorization, which is a bit strange because on the left hand side you have multiplicity E, but on the right hand side you seem to be getting different things, right? But are you getting different things? See, eta is an nth root of unity, and n and the degree dp, they share the factor, right? Their GCD is E. So, after a few steps, actually the term eta to the dp, it repeats, and you can show that it repeats exactly with multiplicity E. That is what we will now just check. It is easy to check actually. So, let n prime be n divided by GCD E, d prime be dp divided by the GCD E, and you know that this is true because the GCD of n and dp is E. So, when you divide out, they become co-prime. So, the right hand side in this claim equals going over the etas 1 minus eta ed prime t raised to degree of the point. So, as eta runs over the nth roots of unity, all of them, this eta raised to ed prime or eta raised to e runs with e repetitions. Right. So, what we are saying is that as eta goes over these n roots of unity, eta raised to e, since e shares, I mean e divides n, what eta raised to e is just a root of n primeth root of unity, and so you will actually see things repeated e many times. Right, every value gets repeated e many times. D prime is co-prime to n prime. So, if you raise this to d prime, the same behavior can be seen. So, eta ed prime runs over with same number of repetitions. So, that is all. Okay, so, that tells you that yeah, that multiplicity is coming out to be e. All we have to check is whether the base is also correct, t raised to n d by e. So, let us also verify that. So, for that essentially what you can say is you have a product. So, you get eta prime t raised to dp can I say this? This whole thing raised to e. I hope this is correct. Right. So, eta raised to ed prime is nothing but this eta prime, which is n primeth root of unity. You go over the distinct ones and then raise the whole thing to e. That is the repetition, that is the multiplicity. So, what is this now? The thing inside. I guess that should just be t raised to dp raised to n prime. Whole thing raised to e. Right, which is as promised. So that's the left hand side. Is it fine? Yes, so we have verified this factorization via nth roots of unity, and this basically tells you about the zeta function. So the contribution of P in this zeta function substitution is exactly this. Which which is already the factorization of z of t comma c. Okay, because this 1 minus eta t to the dp inverse is the contribution of P in this particular substitution of z, which is z of eta t comma c. So we had checked the contribution in all these z substitutions and the product match. The product matches with the left hand side. Is that fine? Okay. Yeah, so we did this mainly to understand delta, and how will this help? So the corollary of this is that there are exactly two poles. Delta is equal to 1. Okay, let's prove this. So the functional equation calculation that we did it basically tells you that the zeta function, after you do the infinite summation, the series summation, it is some polynomial LT by 1 minus t raised to delta times 1 minus qt raised to delta. Where LT is an integral polynomial in variable t, right? This we had yes, I am not saying anything about the degree of L. I am just saying that the denominator only consisted of these two things, 1 minus t delta and 1 minus qt delta, which is easy to check. Yeah, so now we want to use this base change theorem. So we should change the base to what? To get some information on delta. So here is the interesting trick. So let's base change to to n equal to delta. Okay, so this delta, so remember that this is happening in over integers. So it's not clear why we should pick this as our base change, because there the field was fq and we are going to fq to the n. So now I'm saying that instead of fq to the n, you go to q to the delta. Okay, that's, and then apply the base change theorem. So what you will get is the following formula: zt raised to delta c delta is equal to product of eta to the delta equal to 1. So eta is a deltath root of unity, all of them. It goes over all of them, zeta eta t comma c. And what happens here? So something interesting will happen now, which is that when you substitute eta t, replace t by eta t, the denominator will not change. That's why we did this. So you will get L of eta t, that changes, but not the denominator. Right? So which means that you are getting essentially numerator is product of L eta t over all eta. So this will become t raised to delta. That's not very important. What is the only important thing here is that the denominator gets exponentiated. So you get this. That's the important thing. So in the denominator you are getting now you are getting essentially poles with multiplicity delta. Correct? And why is that a problem?
Because left hand side has order 1 pole, right? T equals 1.
Yeah, so left hand side we have substituted t raised to delta, so we have to deduce that carefully.
You just substitute T raised to delta in the above formula.
Above formula, yeah, with a different L. So let's do that carefully. So say so on the other hand, z t delta c delta, this is some other L prime function where you are substituting t raised to delta, and in the denominator you have so let's not do this in one step, let's do it in 2 steps. So the zeta function for c delta looks like this. Which implies that the zeta function substituted t delta for that curve is L prime t delta. Correct? Okay, so yeah, we have these 2 expressions. The place where you will get a contradiction is that in this one all the poles are simple. which has simple poles.
When we go to from C to C delta, doesn't that delta value, like the class group to the image delta change? This is always the same.
Yeah, that's why the numerator is changed. Denominator is always the same.
I mean, that T is to delta that came that time, T is to delta prime something, right? That T of C delta was minimum degree.
Yeah, so his point is correct. But let's yeah, which is why this needed to be done carefully. So let's do that. Let's call this delta prime. But still it should be okay. Do you see that? Right? So we are doing this properly now. This today I think the projector is not good. Doesn't show the colors. So even if it is different delta, the form is this. So when you substitute t raised to delta in this form, you see that there are more poles, but they're all simple. There are possibly more poles, but they're all simple. So there is no repeated pole. While in this expression, you seem to be getting multiplicity delta. So the only way to have this is delta equal to 1. So the thing we had is q minus 1 zt in the functional equation calculation. If I multiply it by t minus 1 and then set t equal to 1, we had seen that we get the class number hc as delta is equal to 1 now. So in the calculation we had this hc over t minus 1, right? So if you clear out t minus 1 and then set t equal to 1, then you get the class number. And now you can get information about LT. So this means that q minus 1 times LT 1 minus 1 minus t is gone, so you get 1 minus qt minus 1 at t equal to 1 is equal to class number, which means that so in the left hand side q minus 1 will cancel, so you get that L1 is equal to hc. Okay, so L of 0 is trivially 1, but L of 1 is an interesting invariant. It's the class number of the curve. So that's an interesting fact. So let's collect these facts in a major theorem. So the properties of L functions are well, this is simply the property of the curve, not of L function, but we have showed it using this as an intermediate function. So the following sequence is now exact. Right, so this was the containment and this was degree. So the degree on the class group is surjective. Okay, so the content here is that there is a a divisor whose degree is 1. That was the only thing missing in our understanding, so now we have that. There is a degree 1 divisor, and it's true over any field of constants. You can take the finite field Fp and it's true. Second property is which we just saw, that the zeta function is LT mod 1 minus t 1 minus qt, where LT is integral and its degree is equal to what? So now with delta equal to 1, you can go back and check the functional equation calculation. There was this 2g minus 2 appearing, and there were things in the denominator, you multiply by them and 2g minus 2 becomes degree 2g. So degree is equal to 2g. And it satisfies the functional equation version, which is this. This also you can check. The calculation which we did just clear away the denominator, and the functional equation for z gives you the functional equation for L, which is qt square raised to g. Okay, that's how L function transforms, which is a polynomial, by the way. It's a degree 2g polynomial. So that you can also deduce from here. There is this t raised to 2g appearing, so it makes sense. That can only happen for degree 2g, because you are substituting basically 1 over t on one side, and yeah, L0 is 1 and L1 is class group, the class number. Okay, so these are the properties of this L function. Any questions?
Do we know how to calculate like this degree 1 point in the curve?
Yes, that's a good question. I did not think of it.
So I think you can sort of sample if you have like random points with LCD being different, and you just force it to become one. Just take two different points of covariant degrees.
Yeah, that's a good point. Yes. So even if this degree was even if delta was not 1, right? Suppose you wanted to reach this delta degree divisor. So what you should do is that you just sample two random points, and then you consider P1 plus P2. Actually, P1 will have order something. P1 will have degree D1 and P2 will have degree D2. And you use Euclid's algorithm to express D1 D2 as a combination equal to delta. So suppose A1 D1 plus A2 D2 is equal to delta, then the divisor should be A1 P1 plus A2 P2. And same thing will give you.
Those are like abstract points. This is an actual point that is degree 1.
No, that is not the claim.
I understand that, but is
Is there an actual point? No, this is a claim only for the class group. So what you are saying is not true. No. It's yeah. It may not even be, actually, yeah, it may not even be sum of actual points. The divisor may just be a sum of prime ideals. And you can use, since you can use positive and negative integers, you can just get what Euclid's algorithm does. Yeah, that is the correct way to understand this. See, asking anything about actual points is very hard because we have not proven Riemann hypothesis yet, right? So we don't know whether these actual points even exist. Your curve may have nothing in the field of constants k. So you have to go to a very big field. So unless we prove Riemann hypothesis, I mean all your questions are kind of doing that. They are jumping to the hypothesis. Yeah, so let's just keep that as computational questions here, that compute a divisor D which is in the pre-image of 1. Right, so that would be basically sampling just they are not 2 points but 2 prime ideals, and you have to do this. Still, you have to do this. Yeah, it is not immediately clear because you may not have actual points at all. So since you don't have actual points at all, then you have to sample somehow prime ideals, or you wait till we prove Riemann hypothesis, and then we'll actually get a lot of points in the base field, and you can actually sample from there. That would be the correct algorithm, but then you have to wait for that. Second question is, can we compute LT? Given, of course, the curve over the field of constants, right? So we know that we observed when we proved Riemann's theorem that genus doesn't happen to be too big, and computation of genus is possible efficiently. So in terms of degree of the curve or degree of the planar representation of the curve, genus is maximum quadratic. So the degree of L is not big, it's just quadratic in the input. So we are asking two questions. How big are the coefficients of L function? Because if these coefficients, which are integers, if they are too big, then you cannot even output them, right? So how big are these coefficients? If they are small, can you compute them? Right? That's the second question. That's a harder question, and as Madhavan will tell you, there is no solution known. So even after a lot of work, there is no algorithm to do this. Best you can do is exponential time algorithms. Even that is not clear. That will get clear only from the hypothesis, because if nature was too bad, if these curves were too bad, then the coefficients of L could have been doubly exponentially big, and there is no way to output that.
Is there even something which is sub-x in both genus and which is what we were trying to do, but apart from that, you're always bad in one direction.
Yeah. So these questions, the second question is definitely open. The first question will be easy once we have Riemann hypothesis. Also, this question will be easy, that L function has small coefficients. So one can present them efficiently in the output, but we don't know how to compute them. Presentation won't be a problem. Okay, so yeah, so now let us come to this hallowed connection to counting points on the curve in the field of constants, right? So what is that to do with the zeta function? So I mean, the way we have defined zeta function is the way Riemann defined his function, which is via this sigma 1 over n to the s, and in our case it's sigma t raised to degree of the divisor. Divisors are like numbers. So in Riemann's hypothesis also it is not clear how does his function connect to counting primes, right? There is a systematic way to go from there to counting primes. Similar thing we can do here. It will be easy algebra to connect our zeta function with counting actual points on the curve in the base field of constants. So let's do that next. So start with the Euler product. So Euler product, which we have been using all the time, says that so let me shorten this to just z. Z will just be the zeta function of curve C, field of constants K. It factorizes as this. So this is almost by definition. This is not a, I mean, we have seen this when we defined the zeta function. Sigma t raised to dp, sigma t raised to d of a divisor, go over all the positive divisors. That factorizes as this over points. That is why in fact we go over non-negative divisors, so that that thing will ultimately resolve itself into points. Now this is a strange product because the points which are, I mean, even the prime ideals, they are infinitely many, right? So you are actually multiplying infinitely many things, but you can see that everything is well defined. There is this notion of convergence in the power series, so it's okay. You can actually do the multiplication. So next thing which we will do is something even more strange. We will differentiate this identity. Okay, so it's already an infinite product, but let's make it even more strange by doing actually two operations. Let's apply log and then the derivative. So use the logarithmic derivative So what it does is that you take log both sides and then you differentiate with respect to this only variable t. So what does that do? We are doing this so that the product, I mean log of product is sum of logs. So you convert product into sum by log and then you differentiate. So let's see what you get. So let's not worry about z for now. So d log of z is equal to, go over all the points, sum, the summand is d log of 1 minus t to the degree inverse. Okay, so right, so what, just remember this identity, d log of a function is equal to f prime over f. That's what we want to use. Right, so left hand side has become z prime over z, and here you will get the derivative of this 1 minus t raised to minus 1 divided by itself. So let's do that. So what is the derivative of this? Minus 1 times dp times t raised to dp minus 1 divided by itself, right? Okay. What is that? Oh, sorry, something I messed up. Minus 1, then you get 1 minus t is dp minus 2. So you get 1 here actually. Okay. There is a minus 1, so when you differentiate, then you will get minus 1, but minus 1 will become minus 2 in the
I
exponent.
think you could take out that minus 1 by using log itself.
Yeah, but let's not do that. So this is just using f prime over f, that's all. No further tricks. So it becomes this, and there is no minus 1. This also is not there because
It's cancelled.
yeah, minus 1 times minus 1, the 1 minus t raised to dp gives you minus 1 also. Yeah, so this is the expression, and right. So how do I want to see this? I want to see it like this. Go over all the points. Degree of the point times go over all numbers. Okay, so sigma dp is out and T inverse also. So now what we are doing is T raised to D divided by 1 minus T raised to D. We are just expanding it into again back to power series, right? So you get powers of T raised to D. So T raised to n times D, n starts with 1. That's what it is. And whenever you see summation, you try to swap it, right? So let's swap this. So what will you get? So this is T inverse times sigma. Suppose I went over numbers m to get T raised to m. So what is the coefficient of T raised to m? What is it counting?
Some t divided.
Yeah, so let's go over numbers first and then look at what points it is counting. So T raised to m will be counted, will appear here only when d of p divides it. And it will then come with dp, right? So the coefficient, I mean in simpler terms, coefficient of T raised to m inside this inner sum comes from those points such that their degree divides m, and the contribution, the weight of that is d of p. That's what we have just swap the summation. And so what is this? How can you now read this off?
This is the number of points of C over F cubed to the
In the finite field of size q raised to m. Is that clear? So if the degree divide, so now think of the field q raised to m, right, size q raised to m. So in that field, this point, since its degree divides m, that prime ideal actually completely factorizes. For that cloud, you are actually in the splitting field, in one of the splitting fields. So, and how many factors will you get? Exactly d of p. So all the conjugates, they are present in this field which is of size q raised to m, right. So you are actually counting points in that field, that's all you are doing. So which is then the number of points in that field. Okay, so nm is the number of points in the curve over that constant. That's all, right? That's all you have on the RHS. So essentially now there is this mysterious connection between the zeta function, the way we defined it from first principles, to the generating function of points that we wanted. Right? There is this neat connection. So yes, so let's just finish this. So let's integrate it to remove the d on the left side, the derivative. Zero to t gives so when you integrate 0 to t, d log of z will become log of zt. Sorry, while the right hand side will become what?
T to the n
There is t raised to m minus 1, right? So this will just become t raised to m by m, m going from 1. Yes, so yes, that's it. In other words, if you don't like log, then you have to use exp. So exp of sigma okay, so that's the connection between the ordinary zeta function definition and the generator that you would want. They are exponentially related. Okay, so this is brilliant. It's especially brilliant because zt we have written as an L function. It's Lt over 1 minus t 1 minus qt. So now if we also expand Lt using its roots, we'll get a magical result because so we use the first identity. So log of Lt you express as a product, so you get sum of log of the factors, and you compare both sides and you have a formula for nm. So let's do that. So now use the fact that zt is equal to Lt over 1 minus t 1 minus qt. Further, don't think of Lt as a polynomial, think of it as a product. right? It's a univariate, so it completely factors. We don't know about its fundamental properties. Maybe its roots are not simple, the roots repeat and so on. But anyways, over complex there are roots, so let us just factor it into that. You know how many roots are there with counted with multiplicity, so that's 2g many roots, its degree is. So I'll write in a different way. I'll write like this. And the reason will be clear soon, because I basically want to apply log both sides, right? So if I write like 1 minus alpha I t, then log of that I have a good expression. Instead of expressing this as t minus alpha I write 1 minus alpha I t, so the log will act better.
You can do this because 0 is never a root.
Yeah, so alpha I are complex numbers. And let's check. So why can I invert the roots?
L of 0 is
Just,
1.
yeah, just that. Correct. So roots of L are actually units in the complex field, so you can invert them. So that is what we have done. So these are actually inverse roots of L, inverse zeros of L. Yeah, so now Z is also actually a product which will help in the first formula. So let's plug it in. So what we get is now log of 1 minus alpha I t I1 to 2g, that's the L part, L function part, minus log of 1 minus t minus log of 1 minus qt, and this is equal to sigma nm, the generating function essentially. Right? So now from here you can read off formula for nm, which is nm is equal to q raised to m plus 1 minus sigma of Li to the m. Right, that's the formula. So 1 by m can be, I mean basically just in the log you recall log of 1 minus t is or minus of log of 1 minus t is just t plus t square by 2 plus t cube by 3 and so on. So t raised to m by m is present everywhere. So forget that, and then nm is just equal to this q raised to m plus 1 coming from the denominator of the zeta function. And the interesting part is coming from the roots of the L, the inverse roots of the L function, and 2g many. So this part alpha I to the m is viewed as the error term. Why the error term? Well, because if this was not there in the projective line, curve has q raised to m plus 1 points, right? So that's another way to see this. So this is the projective line. Plus error. So projective line has q raised to m plus 1 points, right? This is oh, the point at infinity is the plus 1 and others are from the affine. Yeah. Yeah, so this is the error is 0 in the case of only in the case of projective line. For all other curves, smooth projective curves, you will have some error term, plus minus. So since you are summing up over complex, actually I should have said sigma alpha I or sigma alpha I to the m, since this is coming from an integral polynomial, it will always be real. In fact, it will always be, in this case, integer. So this integer can be positive or negative or 0. So when it is 0, you get that's the case of projective line. In other cases, you will be slightly above or less.
I think we get 0 in when it's not a line also.
Yeah,
We have an elliptic curve.
that is true, because it's a statement for all m. Yeah, so in small m, weird things can happen. But if it's true for all m, then your curve has to be the line.
Is that
Yeah, so the question is fundamental question that was asked more than 100 years ago is, how big is the error? So what is your guess? So how big can the error be? Right, so there is, so the version of Riemann hypothesis basically says that the error cannot be too big. In fact, the error term will be square root of the main term. Okay, it's bounded by square root multiplied by the genus G. So it very nicely gels with what happens over numbers. So over numbers also, the estimate of primes, the error term is conjectured to be square root of the main term. Same thing you would conjecture here. The difference is that here we will actually prove this. In fact, we will prove something very strong. We will prove that alpha i's are not arbitrary. So alpha i's themselves will prove that their norm is very special. It's equal to square root of q. So that's the Riemann hypothesis version we'll prove. Okay, one last thing I want to say is by this functional symmetry, we immediately get the following observation, the property that we can label alpha i's such that alpha I times alpha I plus g is equal to q. Let's just see why that is true, that you get immediately actually from the symmetry. So the symmetry basically relates L of t with L of 1 over t, right? So if alpha I is a inverse root, then it says that there is this other inverse root which I am calling alpha of I plus g, such that the product is Q. This follows from the symmetry. So you have 2G roots, you can label them and you can arrange them so that pairwise this property holds. Yeah, but as I said, so Riemann hypothesis, when we'll prove it, we'll actually prove something very powerful. We'll show that actually the norms of these two are equal as well. So we'll show that the norms are equal, which means that the only option is square root Q. Okay. So it is a part of the symmetry. I mean, you can try to guess it from the symmetry, but it's far more. So I don't know why people would have conjectured it. So,
This thing is amazing because now this is what causes in our Jacobian discussions.
mhm.
We have to find this other pair so that everything becomes the Tate pair becomes one, right?
Yeah. So okay.